Good morning, everyone. In today's video, I'm going to show you engineering format and also kind of teach you a little bit about linear momentum when you're dealing with fluid flow. So here's a particular problem that I would give my students. So we have an elbow here, shoots water in right here. All right, we kind of cut the pipe right here. It's a 90-degree elbow. Then it shoots out to atmosphere. Give you some dimensions. And then here's like the word problem. And I also give them the solutions at times to help them to make sure that they know what they're doing. So what I tell students to do first is read the problem carefully and either do two things. Rewrite the problem on engineering paper, and I'll show you that here in a second. Or they can take this and print it on engineering paper. All right. So what is engineering paper? It's this. It's this green lined light end here. This is dark. You write on this page. Don't write on this. It's too dark. We can't see very well with that. So write on this side. And you will notice these boxes up here. These are important. All right. So let's get started. So what I did is I ended up printing that problem right on engineering paper. So here is the problem. Here is the sketch. And you don't have to. You can rewrite the problem or do a quick problem statement and then draw the sketch. Sometimes the sketches are tricky to draw, so just draw them on here or print them on here and you'll be fine. The reason why is because we're going to label a free body diagram on here. So this is going to get involved. Okay, so again, first option, rewrite the problem or print this on engineering paper. All right, so now I'm going to show you my solutions and go through how I did everything, so you know exactly what engineering format is and what we require of you. Boom. So let's start right up at the top. Nothing goes in here but the staple, top left. That's where your staple goes. Your name, the date. This is called intermediate fluids. MEC 341. Homework 4, what problem number you're doing. And then over here is the full page number of your entire homework set. So I only did problem 1, but I just want to show you it's 6 pages for problem 1. But if you have 20 pages, then it's going to be 1 over 20. All right. So this is the top of every engineering paper that you have. All right. So here is this problem. Here's the sketch. I labeled it problem, underlined it. I labeled it sketch, underlined it. So I'll read this. So a 90-degree elbow and a horizontal pipe is used to direct water flow upward at a rate of 40 kilograms per second. That's a key thing, so I underlined it. The diameter of the entire elbow is 10 centimeters, so 1 and 2. The elbow discharges water to the atmosphere, so we know that the gauge pressure is 0, and then the pressure at the exit atmosphere because it's atmospheric pressure. Elevation difference between the centers of the exit and the inlet, 50 centimeters, which is the radius. That's why I labeled Z1 and Z2. I put a datum to reference that Z1 is at 0, and that's all the way up 50 centimeters. The weight of the elbow in the water is neglected. Okay, so we're not including those forces on here. Otherwise, there would be an arrow down. And we want to find the gauge pressure at state 1 and the anchoring force needed to hold the elbow. All right, so a lot of keywords. Over here, again, I labeled coming in state 1, going out state 2. You can put V1 and V2, it's up to you, but I labeled them. I put in a coordinate system, X and Y, straight edge. And then I labeled my forces. So this pipe is cut here. So there is a pressure force times an area, okay, that's causing this flow to go this way. And it's acting perpendicular towards this control volume, which I've created as a dotted orange. And then over here, there's a pressure force here going down. And again, it's perpendicular to this control volume. Okay. These are our anchoring forces, FRX and FRY. These are the forces hold that elbow into place. Otherwise, it will bounce around if it's not anchored correctly. And we need to know these forces in order to size whatever piece of, say, bracket that we need can withstand those forces. So we got to know these forces. So again, labeled problem, underlined keywords, labeled sketch. I used straight edges in all of these arrows. If you notice, I did color pencils to help me identify forces. All right. So now we have the problem in the sketch. There's a lot of information already extracted in your brain. And now what you need to do is you need to write down the givens, write your assumptions, and nomenclature. So over here, in properties, properties you can put into your givens. And I'll talk about that in a second. So givens, variable form, so m dot, 40. Diameter, 0.1 meters. Gauge pressure at 2 is 0 because it's atmosphere. Z1 is 0 because that's our datum. H equals the radius, 0.5, which is the altitude of Z2. Variables, units, numbers. Well, what are those variables? That's what the nomenclature is for. Mass flow rate, density, acceleration due to gravity is g, and so forth. Assumptions. These help us solve the problem and sometimes make it easier to solve the problem. And it's used to identify equations that you can use. But first, we're neglecting the weight of the elbow and the water inside. So that's why I didn't draw an arrow down and call it W. We could have. All right, if you want to. Sure. Where did my straight edge go? Probably be like somewhere right here. I can do an arrow and call this W. Okay, but we're neglecting this, so I can just put an arrow right now through it. That's fine. Okay. This beta with this linear momentum, don't worry about it. We're not going to do anything with it. We're just going to assume it's 1. That's all I'm going to say. We're going to assume that it's steady state, meaning that the flow rate is always going to be 40 everywhere at all times. Okay? It's not going to change. The water is incompressible, all right, meaning we can't change its density. We're neglecting any frictional forces. And this elbow, this control volume, is not moving around in space. It's stationary, so its acceleration is 0. Okay, we're going to need to know that. Now I put properties. Well, what are properties? These are values that are found in tables or constants that you can find easily, or things that are you just use in a typical equation that doesn't change. Like acceleration due to gravity, 9.81. Pretty much we use that number all the time, meters per second squared. Density of water we can use as 1,000 kilograms per meter cubed. It didn't tell us the temperature, so we can just use that. It does change based on temperature, but this is a property we could find if we needed to on a table. Now, I labeled problem, sketch, given, assumptions, nomenclature, properties. The last thing we need before our solution is what are we looking for? Our find. Gauge pressure at 1 and our resultant force. Okay. Now, as you can see, I have in between these green lines, I went kind of down the page nice and neat. I like to have like these set up like this, where my find is below all of these. You could go all the way straight down, but I like to fill this in. However, when you get to the solution, that's down the page. Okay, you're going to see what I'm talking about here. So this is how you initially set up the whole problem in engineering format. You've clearly identified everything that you need to know to do the problem now. Or you think, that's fine. You can go back and say, oh, I forgot this force. Draw it in. Okay. If you notice, pencil, pencil, pencil. I use this pencil. Just make sure it's sharpened. I have a nice eraser. If you notice, I've been erasing, okay, but I can still see my writing. All right, now let's get to the solution. So when you get to the solution, every time you have an equation, I want a heading. Okay, so we're going to start right off with basically what we call Newton's second law or linear momentum, because we're dealing with fluid flow. And we have two directions. We have the x direction, positive right, y direction, positive up. Okay, so sum of the forces in the x equals max plus the summation of beta m dot vx out minus summation of beta m dot vx in. This is all the forces that are drawn on the sketch. This is your acceleration term, but the elbow isn't moving, so it's 0. And these are your, basically, if you want to think about it, forces due to the fluid. So we need to look at all of the out terms in the x and then the in terms. There might be more than one if it's like a y or something and you have multiple values. But in this case, if I go back up to my sketch, I'll screw this down a little right there. If we look at our dotted orange, there's only x coming in, which is this one. Okay. There is no out arrows for velocity in this sketch. Okay, it actually curves up. All right, so we have some of the forces in the y, which you'll see here in a second what they are. Acceleration term in the y, but it's 0 because it's not moving up. It's stationary. It's not accelerating. And then here are our fluid forces out in the y and in the y. Well, if you look at, again, look at the sketch. There is no arrows going downward into the control volume. It's only going out. Okay? So you have fluid coming in here in the x, and you have fluid going up in the y. That's it. So in, out. That's why down here that term is gone and that term is gone, and you only have those two fluid forces. Okay? Again, nice and neat. I labeled with a straight edge. So main equation for linear momentum, x and y. I canceled stuff. The next line down is where we break up these components, these sum of the forces, these summations. Okay. So here we actually have two forces. We have the resultant force in the x, and we have our pressure force. And then here is negative beta m dot v1x. Okay. Over here, we have negative P2G A2, but this is gauge pressure is 0 because it's atmospheric. So we have the resultant force, beta m dot v2y. We could also, if you wanted to, put minus w here. And that was the weight of the elbow and the water, okay, combined, but we're neglecting that. So that could actually go to 0. Okay. And again, go back up here. See how we have this pressure force in the X? That's in the X. There's no other forces in the X but the fluid, but that's on the right side of the equation. And then in the Y, we have this force here going down, and we have Fry going up. But again, that term is 0. We also have the weight, but that we neglected. So that is why we have these forces, these set of equations here and here, but we neglected those. Then what I did was, next line down, I rearranged and solved for Frx and Fry by just moving things on one side of the equation. Highly, highly important that you do these steps clearly. Label, identify X and Y, main equations, write down the next line what you can break these components up into, and then after that, solve for what you need. Now, we can identify that we need to solve for m.1, v1x, p1g, a1, and m.2 and v2y. So what we're going to look for is going to have a heading, solve or find or m.1, m.2, and all of these. Okay? So let's do that. So this is page 1. Page 2, again, I have my heading up here. We're going to solve for m.1 and m.2. We're going to use conservation of mass at steady state, which states that the summation of m.in equals the summation of m.out. We only have one m.in, which is m.1, and one thing out, which is m.2, and that we're just going to call m dot because we have that in our givens. Cool. We're going to now solve for v1x, which is, we're going to use the mass flow rate equation, which is m dot equals rho AV, because we know the density, the mass flow rate, and the area. Okay, so we rearrange that equation to solve for v1 by just dividing by rho A, and we plug in what the area is, which is pi d squared over 4, that equation. Why did I not just give you this equation? Because you should memorize this equation. Mass flow rate is rho AV. So always know the fundamentals first, and then show me that you rearrange it. Okay? Again, I'm going down the page. I have everything in the givens from these equations, so I can plug numbers with units. I solve for V1, which is 5.1 meters per second squared. Okay. Now we're going to use Bernoulli's because we need to solve for P1 gauge. That's our next unknown. Why can we use this equation? Well, if I go back to our assumptions, steady, incompressible, and neglecting friction, we can use Bernoulli's, which is an energy, basically energy balance between two different states, state 1 and state 2, which relates pressure, velocity, altitude from one state to the next. So it's potential energy, kinetic energy, and pressure energy. Okay, so this is the fundamental equation for energy balance using Bernoulli's between two states if it's fluid. State 1 is always like where it starts, and state 2 is where it moves to. Okay. Now, V1 and V2 I canceled because I know that they're the same diameter, so they're going to be the same velocity, and I'll prove that here in a little bit, that they're the same. Our datum was at state 1, so that's 0. And we're gauge pressure at 2 is 0 because it's atmospheric. So we've canceled, but you've identified your main equation, which is Bernoulli's. You have to. I rearranged and solved for P1 gauge, which is rho GZ2. Then I plugged my numbers with units, and I boxed my answer And I boxed it with, I believe, my stencil, nice and neat, like that. Okay. I boxed this one and not these up here because that's what we're looking for. That was in the find. Again, down the page, between the lines, pencil, straight edges, nice and neat. Last thing on this page is we needed to solve for the area. Okay. And again, heading, because we're looking for area. Heading, we're looking for P1G. What did you use? Bernoulli's. Okay. This is just area. That's a fundamental equation. Okay. If you notice up here, I labeled mass flow rate. Okay. Conservation of mass. Let's go to page 3. See, I have the page numbers. In this problem here, I'm solving for V2Y. Okay, which is just V2 for now. We know that the mass flow rates are the same from the previous page. We know that they're rho AVs at each state, and then it verifies that V1 is equal to V2 and so forth. Okay, because it's this densities are the same, the areas are the same because the diameters are the same. Okay, so now we've had, if I go back to page 1, I have this, check. I have this, check. I have this, check. I have that, check. I have this, check. I have that. Boom. Now I can solve for FRX and the X, FRY and the Y. Plug our numbers, our units, and we end up getting 242 newtons in the X, 204 newtons in the Y. Now, I haven't done units yet for a tutorial, but a kilogram times a meter over a second squared is a newton. Okay, that's something that you're just going to have to learn, and I will do a video on that. Okay, so again, down the page, headings, straight edges, down. So like, don't tell me that this equals 204 here. Do it down on the next line, please. You see how I just put it down on the next line? That's what we want. Now, that's just X and Y, but I'm just going to pull this. We're looking for the total resultant, so you have to use resultant force equations, which is FRX squared plus FRY squared. Plug our numbers. We box 316 newtons. And then I need to find the angle, and I also boxed that, even though it didn't ask for it, but we needed you need to know that. You need to know that this angle acts at 40 degrees, 316 newtons. Okay. So if I go back to the sketch here, so it goes over and up, and the angle that it makes right here is theta, 40 degrees. Okay. So this is good because you can always fix it. Angle. Okay. And if you want to draw it on here, where did my ruler go? See this? This goes over. Then this would actually go up. Okay. So then you would have something like, I'm not sure, it probably will act right there. So we can probably just put an arrow here. Okay. That is theta there. Okay. Now, it wasn't looking for that, so that's why I didn't put it in the sketch. But just to give you an idea of where it would act. Okay. Again, we didn't put it in our find, but it is good to know what that angle is acting at. Okay. Again, we can take that out. We didn't need to box it. That's just an optional thing, just to make sure you know, okay, what angle are we at. So if you got rid of that, that is pretty much what we need to find. Again, so here is 3 pages of the format that you need to do. That's called engineering format. Okay. Now, I also did a little script coding, okay, example. So here's my header for that, my nomenclature, my givens, properties, and then I got right into the solution, and I'm trying to solve for FRX and FRY. Here's FR, here's my angle. Okay, I'm going to print out when the mass flow rate is 40 what these answers are, but I also did a graph to show you. Okay, so again, this is an example of a code with correct format. Your heading, nomenclature, you labeled givens, you have units in here. It's straight down, easy to read with variables. These are all variables down here that you can then, if you just change the givens, this would immediately change. And every page should have your, like these external pages should be your name and what the homework is. Okay, and again, I labeled it page 4. Here is the graph, correctly stapled. You see how it's away, like the staple's up here, so I can turn it so I can make it look nice. And again, I have my name. All right, again, I have a nice title. I've labeled my Y, labeled my X. I have a nice solid line that's easy to read. I have my grid on. Okay, and then this is, again, my name, page number, and this is the command window that I spit out the answers to. FR at the angle and your gauge pressure. Okay, and again, I'm using Octave for this coding. It's free, and I have a whole tutorial series on that if you're interested. So this is engineering format. Okay, if you have questions, please let me know, and best of luck.